Yeah, thanks a lot for having me here today. And yes, so despite the title, this is a coding theory talk, okay, but it's not the coding theory that you may be used to, okay, so it's a sort of a different one, different flavor. And I hope I will make you understand a little bit what the problem behind this is. So it's about DNA data storage, okay, and the main topic is about storing information in the form of DNA. And this is not a new idea. It's at least 15 years that people do this, storing data in the form of a macromolecule. But in the last years, the research became much more intense on this topic, both on the side of biology and on the side of information theory. And the main reason is basically this figure. So this is the annual size of the global data sphere. So the amount of data where data is growing exponentially. And this figure does not even take into account the AI, okay, which will generate a lot more data on its own, okay? So that's the problem with the AI. So nowadays, we users generate data, okay? We take a picture and we store it somewhere, okay? We produce a file and we put it on Dropbox, okay? This is how data is generated today. But AI is gonna generate data on its own without us doing it actively, okay? And the same applies to devices, smart devices that you have in your house. When you talk to Alexa, Alexa is doing something and storing a piece, okay, of information somewhere, okay? And for this reason, the amount of data is growing. So we know that the demand projections say that the demand for storage will outpace the supply. So what we need is high density, efficient, durable storage solutions, and that's where DNA-based storage systems come into the picture, okay? So the reason is that DNA as a molecule is extremely dense. And when I say dense, I mean this figure. So 10 billion gigabyte per cubic millimeter of substance. Durable, we can still read pieces of the DNA of mammoths. And you have seen Jurassic Park, I guess. And yes, and it's sustainable because DNA doesn't need to be refrigerated, okay? So it's perfectly durable at room temperature. 20 degrees is perfectly fine for DNA. So it's promising, and this is how very easily, of course, okay? So it's the picture is much more complicated than this, but this is just to give you an idea of how storing the data in the form of DNA works. You have your file, a movie, say, or a TXT in this case. So what you encode it in this alphabet with 4 letters we all know about, okay? Then there is a synthesis part where the data becomes DNA strands, and then you put it in some container, okay? Then when you need the data, you do a PCR, an acronym we all unfortunately are familiar with after COVID. This amplifies the strands of DNA. Then there is a process called sequencing and gives you back the, your strings, and then you decode and you get your file back. This is approximately how it works. Of course, it's much more complicated than this, but this is just, the pieces that you need to put together in order to implement DNA data storage. Yes. Yeah.
DNA, are all strings created equal to as far as the DNA is concerned, or does some make the molecule unstable?
Well, yes, so there is a lot of issues in making when you take data and you make a molecule. So for example, we know that DNA is durable, but it's not particularly reliable. So there are channels modeling this unreliability, and you need in the end to introduce some redundancy to be able to retrieve your data anyways, but that's not what I'm going to talk about in this talk.
No, I'm asking
a
different kind of question. Like, let's say I had a message that had 10,000 Gs in a row.
Yeah.
Would that cause a problem with the molecule?
No. No. I mean, I'm no biologist, but
you would put it through some encoding, so
yeah, exactly.
For sure there's error corrections that they put into the transcription.
Yeah, the mess. Yeah, exactly. So whatever comes out of this process from here, it's something that you can then synthesize. Okay. Yeah. Good. So the drawback of this method is that at the moment, the throughput is quite slow and there are very high costs compared to alternative storage techniques like storing things on a magnetic disk, for example. So the first application that people think of when they study DNA data storage is long-term archiving, and one example is medical records. So say you go to the hospital, you get surgery, you get hospitalized, then a lot of data are created in that moment, but then hopefully you don't need that for the next 10 years because you heal, and then by the time you need next surgery, hopefully 10 years has passed, right? And so we are going to access those data only then. So long-term archiving is the first application of DNA data storage that people think of. And now I'm going to switch topic completely. But it's going to be clear in like 10 minutes why I'm telling you about this. So this is a problem in elementary probability, say, that I think everybody, all of you are familiar with, especially if you are a parent. It's called the coupon collector problem. Okay. So there are breakfast cereal boxes. Yeah. Yes. With virtually unlimited supply and K types of Pokemon cards. Okay, and they are in the boxes of the cereals. Now, each cereal box contains exactly one card. Okay, and the question is, what is the expected number of cereal boxes you need to buy for your kid to collect all the Pokemon cards? Okay, and of course, this depends on the distribution of the cards. And if the distribution is the uniform distribution, so all cards have exactly the same probability, the expected number of boxes you have to buy is this number. Okay, so K times the K harmonic number. And you can use this to estimate, well, the company can estimate how much money they make, from your kid completing the collection. So if a cereal box is $6 Canadian, so I lived in Toronto, but yesterday I checked the price is still current. So it's still approximately $6 Canadian, a box of cereals. And there are 60 evenly distributed Pokemon cards. So Kellogg's can expect to make approximately $282 Canadian for every kid who completes the collection. Okay. But of course, they don't use the uniform distribution because they want to make more money, of course, out of you. And then you can, as you know very well, different cards have different probabilities of show up. This is the general expectation, and then you can play with the, with the distribution and increase the gain. Okay, very good. So why did I tell you about this problem? It's because for DNA storage, a sort of Q analog of this problem is relevant. Okay, so the main difference, which I didn't tell you before, but the main difference between ordinary data storage, so taking files and putting it on a magnetic disk, for example, or a USB stick, and reading data stored in the form of DNA is how you access the data. Okay, and with DNA, and that's something we don't have control on as mathematicians, this is how the biology of this process works, is that you have to read the strands randomly. Okay, so you have to sample DNA. You cannot say, I'm going to read that string. That you cannot do that. Okay, you have to draw strands, okay, until you get the data that you want. This is something you have to work with in this context. Okay, so to be a little bit more formal, this is how it works in practice. Again, this is simplified and everything, but just to give you an idea, is a quite faithful picture. So the information we use to store is represented as a vector x, length k, with entries from a finite field of q. And this vector is encoded via a rank k matrix G, simply by multiplication. Okay, so my x1, xk, which could be a movie, becomes x1, xk times G, which is something else. Okay, and a warning for the coding theorist in the audience: this G is not for protecting from errors. Okay, so if you're thinking of G as the generator matrix of an error correcting code and you would like it to have, for example, large minimum distance, you are on the wrong track here. We're not going to use G to correct errors. We're going to use it for something else. That's going to be clear later in the talk. Okay, so each YI becomes a DNA strand, and then virtually infinite copies are produced. And then to retrieve X, what we do, and that's what you are forced to do, you start drawing with repetition DNA strands, which are your YIs, okay, until, okay, uniformly at random, until you can compute X, okay? And when is it that you can compute X? Well, if you collect the strands Yj with J indexed by a set S, then X can be retrieved if and only if the columns of G indexed by S span Fq to the K. Then you can retrieve your vector, okay? Yes, so this is how it works. And this motivates this problem. It's very easy to state, the coverage depth problem. So E of G is the expected number of columns draws that are needed to span Fq to the K for a given matrix G. And what is the smallest, so you ask yourself, what is the smallest value of EG and which matrix is G achieved? Okay. So the problem is very simple. And this is why I said it's a Q analog, because in this case, you are collecting vectors instead of Pokemon cards. Okay. So you open a serial box and you have a vector of length K over FQ. And your kid completes the collection when the vectors span Fq to the K. Yes, I think kids will find this less interesting than the other one, but maybe some exceptional kid, yes, will like this. Yes, but that's the problem, and we have already solved this problem in a special case when G is the identity matrix, because this is exactly the coupon collector problem, right? What does it mean to span Fq to the K? It means that I collected all the standard basis vectors, right? So the expectation is exactly K, H to the K. And then the question is clear, I think, can't we just, isn't the identity matrix good enough for this problem, right? Well, no, if you want to get the best performance possible. So this example is for K equal 3, the simplest possible. Then if you take the identity 3 by 3 matrix, the expectation is 3H3. We have seen that already, that's 5.5. Okay, so you need to draw approximately 5.5 times. Not exactly 5.5 times, and that's the expected number of columns you have to draw. But if you use this matrix, which is longer, but still, of course, K is equal to 3, then the expectation is approximately 3.92. So it's less, okay? Which means that, so just to repeat again, if you have this matrix and you draw columns uniformly at random, the number of draws you need in order to span FQ with F5 to the 3 in this case is approximately less than 4 draws. Okay, so you ask, of course, how small can this number be? And almost the only known result is this bound by these authors in 2023, and they prove that whenever you have a matrix G of rank K, then the expected number of draws that you need is at least this number, which is NHN minus HN minus K. Okay, these are the harmonic numbers again. Okay. And moreover, this lower bound is attained with equality by any generator matrix of an MDS code, if it exists. So I will tell you what MDS codes are now. Okay. And by no other type of matrices, okay? So MDS matrices, so matrices that generate an MDS code, are the only matrices attaining this bound with equality, okay? I will show a short proof of this later. So why did this problem started to get the attention of coding theorists is because it's not difficult to see that if two matrices have the same row space, then these expectations are the same. So this expectation only depends on the row space of the matrix, okay? And row space of matrices, well, subspaces of Fq to the n are objects that coding theorists know as error correcting codes, okay? So, and since this number only depends on the code, then people started to ask, okay, I know some codes, right? Let's see what type of numbers I get. Okay, so it's natural to look at k-dimensional subspaces instead of matrices. These objects are called error correcting codes, and then but yeah, as I warned you at the beginning, sorry, I'm going, yes. We're not going to use them to correct errors, okay? So that's important. We are using them to retrieve information efficiently. Oops, okay, so I thought maybe not everybody has a background in coding theory, so I included a couple of slides about what error correcting codes do classically. So this is how approximately all digital communications work, one way or another. You have some messages. The first thing you do, you compress them. That's also an application of coding theory. Then you encrypt them, and then you encode them. And the encoding process is basically adding redundancies to data to make it robust to noise. Okay, because then the encoded messages, they go through a channel, which typically has some noise. Think of a space probe sending a signal to the surface of the Earth. The solar wind and clouds are interacting with the signal. That's what we call noise. And then decode. So we exploit the redundancy that you added in the encoding phase to correct, basically clear the noise. Then you decrypt and decompress. Okay, this is how all digital communications work, approximately. Okay, even those that are not, actual communication. For example, taking files and storing them on a USB stick. Okay, in that case, the noise is, for example, your fingers touching the USB, right? Yes. And then in this context, a k-dimensional code C is MDS. These are the codes that optimize the bound that I showed before. If for every x in the code, non-zero x in the code, you have at least n minus k plus 1 non-zero entries, okay, in this vector. Okay. And having more non-zero entries consistently for all the non-zero code words would not be possible, okay? So if you ask that n minus k plus 2 non-zero entries are there for every non-zero vector, that's not possible because there is this simple result by Singleton. It's one of the main theorems in coding theory, that if you have a non-zero code and d of c is the minimum weight, where the weight is the number of non-zero entries of a vector, yes, then this number, the d, is upper bounded by n minus the dimension of the code plus 1. So yes.
Is there something special about 0?
It's a vector space, so the 0 is always in the code. So that you remove from, otherwise the minimum distance would always be 0, because that's always in the space. Yes. So this starts, yeah.
You have the word matroid in your title, but you don't say uniform.
Yeah, but I will.
Oh. Yes.
Yes, that's where we are going.
So
Yes, yes.
Maybe it's a bit of a philosophical question. So you said the matrix is not used with code and dual correction in the classical sense, which I see, but it seems like a deletion problem to me. This seems like a deletion problem, right? You could imagine that you have the vector and then some entries are erased, and then you only have access to the others, and you kind of want to minimize, so you want to maximize the number of deletions that you can recover. It's a little bit different from the usual because you want to do it kind of uniformly all the time. You want to say, I can always do so many.
Let's put it like that. For given k and n, there are cases where the code with the largest possible minimum distance doesn't give you the best performance. Yeah. I think this sort of, it's more precise what I want to say.
Sure.
Yeah.
Sorry, I'm just curious because you're in the definition of what does the acronym MDS actually
Maximum distance separable. Yes. Good. So I recycled this slide from the introduction to a coding theory course I teach at TUE, just to illustrate what error correcting codes do. So MDS codes, the one I just talked about, are behind the QR code technology. Okay, so whenever you use QR code, you are using MDS codes, and the specific type, they are called Reed-Solomon. So the way they work is, well, so if you can check that this QR code still scans correctly, even though I vandalized it a little bit by putting a logo in front, okay? And that's because the QR code adds some redundancy to data, and the noise in this case is, I don't know, some fingerprint you have on your camera, right? Or maybe you had the QR code on paper and it rained a bit, okay? So those type of things. But the third one doesn't scan, okay? That's beyond the correction capability of the code. Good. So this is what coding theory does classically, okay? It corrects errors like that. So, and it's actually easy to construct MDS codes if you have a sufficiently large field. I wanted to tell you very briefly the construction. So suppose your field has a size q, at least n is your length. So you take distinct elements of fq, alpha 1 through alpha n, and then you consider the evaluation map that takes a polynomial of degree strictly smaller than k into fq to the n, and it just evaluates. Okay, so f goes into f of alpha 1 up to f of alpha n. Well then, so if f is not the zero polynomial, then the evaluation of this polynomial cannot have more than the degree of f 0 entries. And therefore, the evaluation has at least n minus the degree of f non-zero entries.
So,
Yeah.
I'm confused again. So
Yeah.
we started with a matrix, and then we said, well, we should really just do this as pointing Ravagnani because you only care about the span.
Yeah.
But now it looks like you're back to matrix again.
Where's the matrix here?
This map,
Yeah.
this evaluation map.
Yeah, it's an evaluation map, yes.
No,
So
I
Yes.
think,
where's
I
the
think,
pointing Ravagnani in the out?
yeah.
The
no,
image.
So, I mean,
I see.
you always represent these objects via a matrix, in any case, even though that many matrices will correspond to the same point, but usually you just look at a matrix.
Yes.
I got it now.
No, yeah. So I don't need a matrix in this case, although yes, it's very convenient, as Elisa says. Yeah. But we're always going to talk about matrices in the end, but I just want to motivate why coding theorists jumped on this problem, why they found it interesting. And it's because it's a property of the error correcting code, really, and not of the matrix G. And then, yes, I wanted to offer some background on coding theory. So classically used for correcting errors, and this is how you construct the most famous ones. Yes, so you have this evaluation map, and then, so we have seen that the evaluation of every non-zero polynomial has at least n minus the degree of f non-zero entries, but the degree of f is strictly smaller than k, and therefore the number of non-zero entries is at least n minus k plus 1. And this observation shows that the evaluation map is injective, which gives you the dimension of the image, and that the weight of every non-zero element is at least n minus k plus 1, and we know by the singleton bound that it cannot be larger. So the image of this is precisely a code, an MDS code, okay, the way I defined it. So it's a k-dimensional vector space of fq to the n, where every non-zero vector has at least n minus k plus 1 non-zero entries. Okay, and note that we heavily used q at least n in the proof. Okay, you need those distinct elements, otherwise the argument breaks down. Very good. So as I said, people started to evaluate the performance of known error correcting codes. We have seen those of MDS codes, but you may ask, and this is something I've worked on with one of my students and a collaborator at Technion. So if G generates, because coding theorists will be curious about this question. So if G generates a query simplex code of dimension k, then the length is bound by the definition, then this is the value of the expectation. And I'm skipping the details. And then the Hamming code is another one where we can compute the performance, although it's harder than with the simplex code. These are the numbers that you get. In general, it's hard to compute, to give closed formulas for the expectation for a given matrix. So I think MDS codes, Hamming codes, and simplex codes are sort of the only codes where this value is known, where a closed formula is known. We are working on Reed-Muller codes, but that's challenging. Okay, so there are many research directions that can be explored in this topic. I'm actively working, as I mentioned, with one of my students on those in black. But I thought that it could be interesting at this workshop, because of the background of people, to talk about connection with the matroids and applications of this connection, for example, for obtaining bound on this value. Okay, and I want to tell you a little bit about that. So as Bernd already said, when I talk about MDS codes, I'm talking about uniform matrices, okay? And the property that you really need in order to compute the performance of MDS codes for this problem is not the minimum distance. You sort of don't care about that. It's a byproduct for you. What you really care about is property 2 of this characterization. So if you have vector space in FQ to the n of dimension k and C is the row space, then the following properties are equivalent. C is an MDS code as I defined it. All maximal minors of C of G are non-zero, and G represents the uniform matroid over FQ. Okay, and yes, properties 2 and 3, they are independent on the matrix that you choose for the representation. And property 2 is key actually for computing the expectation. I will show you in a second why. And we don't particularly care about a minimum distance. So the way I look at it is that, okay, we need this property 2, and then, oh, by the way, these codes also have large minimum distance, but it's not really something that helps you in any way in the proof. And the issue is that for Q small, the uniform matroid is not representable over FQ, okay? This is at the root of a long-standing conjecture by Segre from 1955. It was already proven in many cases that you need Q at least n minus 1. It's not difficult to get a construction for Q equal to n minus 1. I gave one for Q equal n, but there is a modification of that also for n minus 1. The only exception is conjecture to be k equal 3, where in any case you need Q at least n minus 2. Okay, this is called the MDS conjecture, or one of the Segre's conjectures. And yes, as I said, it's proven in many cases, but not completely. For example, if Q is a prime, this has been proven, but not in general, okay? And I think people gave up. It's also not a current problem in coding theory anymore. So people gave up, but also nobody sort of cares anymore. Yes. Very good. Okay. So the connection with matroids, I think it's clear from the, well, this proposition and then another one that I have. So if you have a rank K matrix G and an integer S between 0 and n, so define this quantity alpha GS, that's the number of subsets of 1n of size S, where the columns of G indexed by S span FQ to the K. Okay, you're just counting them. Okay, then you can express the expectation easily in terms of these quantities, the alphas. Okay, so it is NHN, so the harmonic number, minus this sum. Okay, you're sort of averaging those with some, it's not really an average, but it looks closely related to 1. Okay, yes, so alpha GS basically counts the S sets containing a basis of the matroid, which is represented by G. And using this characterization is actually easy, very easy to prove the bound by the people that I mentioned before, because of course alpha CS is upper bounded by n choose S. That's the most trivial bound, right? And then if you plug that into the formula, you get exactly that. Okay, and you also get that the bound is only attained if you have equality in this, okay? Because that's really a sum with the minus in front, there is no alternating anything, okay? So with equality, if and only if G generates an MDS code, okay? So while preparing this talk for this event, I also worked out a different characterization which could be more helpful for us. So you can also rewrite this as NHN minus n times this sum. Now, I nu is the collection of independent sets of rank nu of the dual of the matroid represented by G. And again, if you use the fact that, well, there is a typo here, I nu is upper bounded by n choose nu, you obtain again the lower bound from that we know about, okay? And then in general, minimizing the expectation is the same as maximizing this sort of expression involving the number of rank nu independent sets or cardinality nu independent sets of a matroid. So that's sort of a general question that you can ask yourself, given a non-uniform matroid of rank T, because for uniform matroid we know already the answer, what can you say about this quantity? So you sum over all the, nu from 1 to up to the rank. And then you sort of take this. I put in evidence this because this reminds of an average, but there's this nu in the way, but yeah. And so does this quantity, for example, have a combinatorial interpretation? Does it only depend on the TUT or the characteristic polynomial of the matroid? Can I evaluate it somewhere and get this quantity, right? And something special if M is representable. Can I say something special in that case? Okay, and can I use all of this to establish bounds for this quantity? And then, well, you know much better than me that when you have a matroid of rank K, then the independent sets, they form a simplicial complex. And then if you record the cardinalities of the independent sets, that's the F vector of the simplicial complex, right? And this has been studied extensively with commutative algebra techniques. Yes?
This collective form might make sense for simplicial complexes too.
Yeah, totally. We're removing the matroid. Yes, totally. Yeah. Yes. Yeah. So, for example, it was a conjecture whether or not these numbers they form a log concave sequence, Mason's conjecture, and so that was pretty hard, I guess. And yes, so that I thought this was a good topic for this event because of the background of people. So in the next talk by Diego, who will also introduce a different problem, I guess. But the first part is going to be about a little bit more technical to give you an idea of what a matroid can tell you about an error correcting code. So Diego is going to dive a little bit into, you take a code represented by a matrix, the row space of a matrix, you take the matroid, which is represented by that matrix. So what does the matroid remember about the code? So that's the idea for tomorrow. That's the end.